Here, we explore the key concepts behind momentum and impulse, focusing on understanding their derivation, the fundamental equations involved, and how these ideas apply in real-world situations. This foundation will help us see how forces affect the motion of objects over time and how that translates into changes in momentum. Let's dive into these dynamics step by step. Impulse is a force applied for a period of time. The impulse is also equal to the change in momentum of an object. This means that when force is applied for a period of time, it results in a difference in the object's momentum, which is a vector quantity. The direction of the impulse corresponds directly to the change in momentum. Understanding this relationship helps us connect force and motion through time, giving a clear picture of how objects speed up, slow down, or change direction. Let's take a look at the foundation of this concept by starting with F equals ma. It tells us that force is the product of mass and acceleration. Acceleration, in turn, is defined as the change in velocity over the change in time. This simple relationship helps us understand how objects respond to forces and forms the basis for many more complex ideas we'll explore. Here, we start with the basic formula for force, which is mass times the change in velocity over time. By rearranging, we multiply mass by the change in velocity and then divide by the change in time. Recognizing that mass times the change in velocity represents a change in momentum, we simplify this to show that force equals the change in momentum over the change in time. This clearly states that force is essentially the rate at which momentum changes. This equation shows the relationship between impulse and momentum. The impulse, which is the force applied over a certain period of time, causes a change in momentum. In other words, when you apply a force for a specific duration, it results in a change in the object's momentum. This is a fundamental concept that helps us understand how forces affect moving objects. Here we see how the actual force applied over time varies in a real scenario, shown by the curved line, while the average force is represented as a constant, simplified value. This graph helps us understand that the equation we use works correctly when the force remains steady or when we substitute the actual force with this average force. This approximation makes calculations easier without losing significant accuracy in most cases. We can also consider the area under the curve to be equal to both the impulse and the change in momentum. Let's move forward by understanding how force and time interact when the change in momentum is constant. When the contact time is short, the force applied must be high to produce the same change in momentum. On the other hand, if the contact time is longer, the force needed is lower. This means that spreading out the time over which the force is applied reduces the intensity of the force itself, even though the overall change in momentum remains the same. This relationship helps us see how timing plays a crucial role in managing forces during impacts or collisions. When you hit a ball in sports like tennis, following through after the hit is important because it keeps the force acting on the ball for a longer time. This helps to increase the ball's change in momentum. So, by following through, you extend the time over which force is exerted, resulting in a larger change in momentum of the ball. This sequence of movements in a forehand stroke shows how the racket continues moving after contact to maximize that force and time. When catching a ball, the force from your hands over the time your hands are in contact with the ball affects how much the ball's momentum changes, helping you stop or redirect it smoothly. Catching a fast-moving ball can make your hands sting. You might drop the ball in pain. By drawing the ball towards you during the catch increases the time that the force is applied to your hand, but that force is much smaller. In the sequence of images, you see a person preparing to throw a shot put using the step-back technique. Notice how he gradually shifts his weight backward and then forward while holding the shot put close to his neck. This movement increases the time over which he applies force to the shot put, allowing for a greater change in momentum and ultimately a stronger throw. To kick a ball as far as you can, you need to increase its momentum. This requires a large impulse, a large force applied over a long time. The footballer needs to follow through with the kick. In a car crash, the airbag slows down the forward motion of the passenger more gradually than if they were to hit the dashboard directly. By increasing the time over which the force acts, the airbag reduces the overall force experienced, which helps to decrease injuries. This principle is why cushioning and safety devices are designed to extend the time of impact and reduce the force on the body. In a car crash, increasing the time over which a force is applied can reduce the force experienced. The crash test image shows a car hitting a barrier. The front of the car has a crumple zone, an area designed to compress, slowing the impact and spreading the force over a longer time, reducing injury risks by managing the change in momentum more safely.